Okay, sorry about that last video. Something went wonky. Okay, so real quick, we'll go over it again. So the P waves are what arrive first. They're always that initial wave that shows up, but they have a smaller magnitude. Then after a period of time, your S waves show up. Now, the distance between these is going to be dependent on how far your monitoring station or your recording station is from the initiation of the earthquake. So the further it is from the actual earthquake occurrence, the greater the distance between the arrival of the P waves and the arrival of the S waves. So these are where both the body waves are. Your surface waves arrive after the S waves and are identified by the much higher magnitude that happens in contrast to the S waves. So the S waves are a lower magnitude than the surface waves. This transition here is when you know the surface waves have arrived. So if we're looking at an example, you have 4 houses. You have an earthquake that is instigated under house A. So because of the very short travel time from the earthquake to house A, you're going to get everything kind of right on top of itself. P wave, the S wave, and the surface waves almost all arrive at the same time. Now waves don't travel in just a straight line. They kind of move, curve through the earth a bit. So when you get to house B, everything's moving through the mantle, which is a solid matter. So you're going to get your P waves, and then after a period of time your S waves, followed by your surface waves. So this would be here. You've got the defined difference between your P wave, your S wave, your surface waves. Now house C, you're going to get an arrival of your P waves, and then your S waves, followed by your surface waves. But you've got much further distance to travel here. So your P waves are not going to happen in this first interval. Your P waves aren't going to happen until the second interval. So the only ones left with P waves here are these two. Now you're still going to get S waves coming through here. You're not having to travel through the core to get to house C from the earthquake. So you're going to get some S waves followed by your surface waves. Now to get to house D, you're going to have to move through this outer core to reach it. So you've got your P waves that have to travel a further distance, and because of the change through material, it's actually decreased in magnitude. Now the outer core is liquid, and like we talked about before, S waves can't travel through liquid, so you're not going to have S waves on the readout at house D. So there's no S waves here before your surface waves arrive. So this is just how an example of how these waves are traveled. So your P and S waves straight to house A, your P and S waves straight to house B, surface waves follow. P and S waves, they just barely brush past that inner core or outer core to get to house C, so you've still got both. And your P and S waves hit the outer core, at which point there's a bit of a refraction because of the change in density, change in material, before you start to travel just your P waves, and then change again through that change in density before your P waves reach house D. Okay, so this is a really good image to study. This really helps explain how each of these waves move and the travel time based on the distance from the actual epicenter of an earthquake. And a good way to remind yourself that S waves cannot travel through liquids, so you're not going to get a readout of those when you start to get significant distance away from that epicenter. So now that we've covered earthquakes in general and how we are aware of the Earth's interior, let's begin to speak about rock deformation and mountain building. So in these two images, we've got pictures of fossils that were found at rock outcrops. So what does the presence of fossils of marine animals found in present-day mountain ranges suggest to you? So this is a fossil of a trilobite that's found in Yoho National Park in the Canadian Rockies. And this is, I think it's an ammonite in Andalusia, Spain. So what this should indicate to you is that these mountain ranges were once underwater. That's the only way you can get marine animal fossils in these high elevation mountain ranges. So to understand how these rocks that were underwater with marine life ended up at elevations of 4,000 to 8,000 feet above sea level, we need to understand rock deformation. So rock deformation is part of the process that results in fossils on top of mountains. rock deformation can occur on scales of just a few inches to many hundreds of miles. So here we've got internal deformation of a rock. Here's a smaller scale. This is just like a highway outcrop. Here's another outcrop, but it's a slightly larger scale than this one. So this one is, about 30 meters. This one's much higher, a larger scale. And then this is actually an image of the Susquehanna River traveling through south central Pennsylvania. And this is down near Harrisburg, and you can actually see the deformation of these rocks. The different colors are changes in elevation. So these reds are higher in elevation, and these are lower in elevations. So what is rock deformation? Deformation is a general term for all the changes in the original form of a rock body. So anything that changes a rock from its original form is a deformation. So most crustal deformation occurs along plate margins. And why does that happen? So most crustal deformation occurs along plate margins because that's where you start to get forces acting on the rocks, which create the deformation. So the deformation involves stress. Stress is a force applied to a given area. So along plate margins, you've got a force applied to a given area, and it creates a stress changing the rock. So we have three types of deformation when we talk about rocks. Elastic deformation. This is where a rock returns to nearly its original size and shape when stress is removed. So think of like a rubber band or a bungee cord or a spring. You can compress it, you can change it, but as soon as you let go, it goes back to how it was. Ductile deformation is a rock that flows once the elastic limit has been passed. This typically occurs under higher temperature and pressures. So this is where folding happens. So those pictures we saw here, these folds are caused by ductile deformation. Okay, they're past their elastic point. They won't return to their original station, but they haven't broken. They've just remolded. And then finally, we have brittle deformation. This is where a rock fractures or breaks once the elastic limit of a rock has been passed. This is very common at the Earth's surface. So faults are caused by brittle deformation. So San Andreas Fault, other dormant, larger fault lines that we see are caused by brittle deformation. So here we're just going to look at folds. So during crustal deformation, rocks are actually bent into wave-like undulations called folds. They typically result from compressional stresses, which shorten and thicken the crust. So when you've got, like the Himalayas, you've got these converging plate boundaries, and as they converge, they're pushing all that crust material up against itself and doesn't have anywhere to go, so it kind of warps in between and folds and thickens and thrusts itself upward. Folds may or may not be exposed at the Earth's surface, but when we talk about folds, we have to be able to describe the sections of a fold. So geologists typically use two general terms, anticline and syncline. An anticline is the upfold of the rock layer, and synclines are the downfold, or the troughs of rock layers. So if you look at this image, the portion where the rocks got shoved up is the anticline, and then the portion where it kind of warped down is the syncline. So you typically have pairings of multiple anclines and synclines. There are different types of anticlines. Did I call them anclines? I meant anticlines. There are multiple types of anticlines and synclines. You have your symmetrical, which is where if you drew an axial plane, or if you drew a line right through the middle of the peak, it would be identical on the left and on the right. Okay, so like this one right here is identical on the left and the right, same with the syncline. Asymmetrical folds means if you drew a line through the peak, so here we've got our peak right here, it would not be symmetrical. You've got one that's a longer, more gradual slope, and one that's a shorter, more abrupt slope. And then finally, you can get what are called overturned folds. So an overturned fold is where you have such a sharp difference between them that your shortened limb, your overturned limb, is actually starting to be overridden by the other limb. So here you can see the left limb is actually starting to override the right limb. And it can actually, if enough stress is applied, you can actually get a collapse of that overturned limb. So here is an example of an overturned fold or an overturned anticline. So here's our axis, and you can see our left limb is almost horizontal. It's been forced up over it so much. And this is our actual overturned limb right here. So if there was any more force applied, we would actually start pushing this section over and collapsing onto that one. Now, it's very common to see faults start to develop in these regions because there's so much force being applied on it and trying to override these rocks so much that some of that stress is translated down into an area where it is unable to handle the movement, and it actually faults, breaks apart to release some of that energy. Okay, within anticline and syncline systems, we can also get some additional structures. So one is a dome, typically associated with an anticline. This is where you get a bedrock structure that is upwarped in all directions. So when we were looking earlier, it was just kind of a 2D. You know, we had a very elongated upwarping here. So instead of this very elongated upwarping, we have a uniform upwarping. So it's just, you know, the surface kind of bulged up like this. And what happens is, as a surface is exposed upward, you start to have preferential erosion at the higher elevations. So that erodes faster than the material below it. So you actually get an exposure of older rocks in the center with the younger rocks down at the surface because it's been warped down. So as you erode, that older material gets exposed and the younger material stays around the perimeter of your dome system. So we have our oldest rock, and it's slightly younger all the way out to our youngest material right here at the surface. Conversely, a basin typically forms within a syncline, and it's a structure that is downwarped in all directions towards the central area, with the youngest rocks in the center and the oldest rocks at the edges. So this is because basins tend to be depositional zones. So you have your older material up at the edges, but as material erodes at the higher elevations, it is carried down gradient where it deposits within the basin. Okay, so here you have the older material weathering away and being deposited at the perimeter. Here you have the older material at the perimeter moving downslope into the interior of the basin and depositing new material within the inside, giving you your younger strata. You can also get ellipsoidal domes. This is an example in the Black Hills of South Dakota. The oldest material here is a crystalline area, a slightly younger limestone, and then the much younger, I think this is a sandstone outside it. Another example is, or an elliptical basin is actually Lake Superior. You have your older material around the perimeters and your younger strata. If you look at this picture here, so your older crystalline material here and your younger strata deposited inside, and then you've actually got your lake existing on top of it. Not all folds can be detected at the surface, so we have plenty that are visible at the surface, a lot due to highway cutouts. We can see tons through the mountains. But some are, well, actually many are subsurface. They're buried under new layers of sediment and rock. And other, so to detect these subsurface folds or subsurface faults, seismic methods are used. So we use these ground penetrating vibrations, and their reflections back actually tell us the difference in the rock layers in the subsurface. So this is just a seismic data readout, and you can see the colors kind of indicate rock type based on how the waves are returned. And you get this peak here at a depth of, I think it's 1,200 meters, indicating that there is a subsurface fold right here. So this is the same subsurface fold, and what they did is they actually drilled here into this dome or this fold and discovered oil. So this is used to identify these subsurface folds or these domes is used very regularly in natural gas and oil, because oil and natural gas rock units are typically shales or sandstones, but it's important to note that because of the density of the natural gas and oil, they actually collect in these dome features. Okay, so they accumulate in these portions. So this is a really important method for the oil and gas industry, and being able to identify these is extremely important because these domes are areas of a high likelihood of natural gas or oil deposits. So here we're just looking at the types of folds on this image. So A, we would have an anticline, B, we have a syncline, C is another anticline, D is a syncline, E is another anticline. Which folds are not symmetrical? Okay, so I'm going to let you review these. These are, it's the same image we saw before. So when trying to examine folds within a rock system, geologists measure what is called the dip and the strike and the age of the rocks to determine what limb of a fold we are observing. And we're going to cover that later on. I think it's later on in this chapter. Now we're going to move on to a bit just to explore brittle deformation or faults. So faults are fractures in rocks along which displacement has occurred. Sudden movement along a fault is what causes earthquakes. There are two types of faults. Your dip-slip faults are faults where the movement is parallel to the dip or inclination of the fault system or fault surface. So if you look at the photo on the right, you can see this crack right here. That's your fault surface. This is where your rock moves either up or down along this crack. Strike-slip faults are faults where the movement is parallel to the strike or the compass direction of the fault. So this is your dip. So think if you're dipping into something. Whereas your strike-slip fault is parallel to the strike or the compass direction. So, if you're looking, you talk about this in like a north-south kind of deal of the fault surface. When we talk about strike and dip of a fault system, scientists use what is called the right-hand rule. So to determine the dip, you would place your right hand on the plane in question and point your fingertips down the dip of a plane. So if this was my plane, I would point my fingertips down. And you would measure the dip amount with a protractor and a compass. Okay. Then the strike is measured if you extend your right hand's thumb perpendicular to my fingers. While I'm resting on the plane of the dip, your thumb points in the direction of the strike. So you'd measure the direction of the strike with a compass. So if I'm doing this, I would use a protractor to say I've got a dip angle of about 40 degrees. And we're going to assume it's north, south, east, and west. And I would have a strike towards the east. Okay, so a 40-degree dip with a strike, say due east, so it's like a 90-degree strike. Okay, because when you do these measurements, your strike is not the cardinal directions. We're actually doing the degrees. So due east would be a 90-degree strike. So using the right-hand rule, in what compass direction is this fault plane dipping? So if this is our fault plane right here, our fault plane is actually dipping to the northeast, correct? See, that's the closest match angle right here. Because if you put your right hand, it's really hard to do with a PowerPoint slide, but if you put your right hand on it, it's actually pointing to the northeast. Oh, I'm sorry, what direction is the fault plane dipping? Whoops, there we go. It's striking to the northeast. It's dipping to the southeast, okay? So when we talk about fault displacement, it really helps to understand which portion of the rock, or how the portions of rock are moving in relation to each other. So imagine you walk into the plane of a fault surface. So we have a fault system. I'm trying to think of like a helpful visual. We have a fault system. If you're looking straight at it, if you drilled a hole straight into that crack in the center, you would want to know what is the rock unit above you, what is the rock unit below you. So miners would excavate these tunnels along the fault because mineral deposits tend to occur along these fault lines. So you would get a lot of mining activity here. So when you would drill a hole straight in along this fault line, the section above you would be called your hanging wall block because that's where you'd hang your lanterns, and the section below you would be your footwall block because that's where you were walking. So if you look at this little image here, no matter what the angle is of your fault, you're always going to have one section that is primarily above you and one section that's primarily below you. So you have your hanging block and your footwall block. So when we talk about these dip slip faults, there are two different types. You can have a normal fault or a reverse fault. Normal faults are where the hanging wall has moved down in relative to the footwall. So if you have two blocks here and your hanging wall slips down, okay? This is the result of extensional forces. So if you're pulling something apart, something's going to drop down, right? So if you pull it apart, there's a unit there that's just going to plop right into that opening. Whereas a reverse fault is where your hanging wall has actually moved up relative to the footwall. This is the result of compressional forces. So do you see any evidence for additional faulting to the picture on the left? So we've got our one fault here. Yeah, we've actually got additional mini faults going on here as a result of the extensional forces. So here you've got your normal fault, you've got your tensional or expressional forces. It pulls down your hanging block in relation to your footwall. Your reverse fault is compressional forces, and it actually shoves that hanging wall block up over the footwall block. And then what we've got are called thrust faults. These are reverse faults, but the plane dips at an angle less than 45 degrees from horizontal. So this is just something for you to do on your own. See how many faults you can identify within this before moving on to the next slide when you review these. There are a large number of fault systems. So here you've got your normal fault. See the red has dropped down below the other red. There you've got a thrust and a normal. So they very rarely occur as just a single. The forces acting on it tend to create multiple faults within a system. So this is actually looking at faults within Western New York. So you can see there's actually a large number of fault systems within all of New York. This is where Jamestown is. The Clarendon-Linden fault zone is actually a seismically active basement fault system. So this is found right, to the northwest, to the northeast of us. And then the Bass Island fault zone is not seismically active, but they are thrust faults that do not reach into the basement rock. So there are actually dormant thrust faults underlying the Jamestown area. So this is just looking at earthquake magnitudes in relation to some of these fault zones. New York has several active fault systems. So I mentioned that a couple seconds ago. A system is a zone of parallel or intertwining faults as seen from above. So in Western New York, the most seismically active is the Clarendon-Linden fault system. It has a strike northward, so the general strike is this direction, and is located 20 to 30 miles east of Buffalo. There has been recorded seismic activity of up to 5 on the Richter scale, and it is extensional or normal faults. So these are from extensional expanding forces. Its vertical extent, it actually originates in the basement crystalline, igneous, and metamorphic rocks and extends to the surface. So basically the deepest, oldest rocks that we're aware of extends all the way from those all the way to the surface. And there are no significant production of oil and gas along this fault zone. The fault movement likely caused any traps that did exist to leak its hydrocarbons to the surface. So these fault systems are not a good source of any sort of oil or gas production. The fault system near Jamestown are the Bass Island fault system. The strike is northeast under Bemis Point on Lake Chautauqua, and occurs in Chautauqua and Cattaraugus counties, primarily found under the Bemis Point on Lake Chautauqua. There's no known seismicity associated with this. They're dormant right now. And these are actually compressional faults created by compression when Africa collided with North America. The vertical extent, these go through the Ordovician shales and Silurian salt beds, so it doesn't reach all the way to the basement, and they also do not reach the surface. So they are very contained within a certain depth of the Earth's surface. However, they do provide traps for oil and gas. This system was active and successfully drilled for oil and gas during the 80s and 90s, and the largest modern oil wells in New York were actually discovered there. If you go up to Lake Erie, just south of Fredonia, I think it's like Erie Park or Erie Point. Anyway, if you go to the shale beds right along the beach there, if you break the shale rocks apart, you can actually smell that gas that's trapped within the shale. So this is just looking at the Bass Island fault trend, so you can see that northeast trend that they have. And this is a geologic cross section of the Bass Island fault trends and thrust faults. So this just shows you kind of 3 different thrust fault systems right within this, I think it's like 4,000 foot range. So strike slip faults occur when 2 fault blocks move past each other along the strike of the fault. Sorry, so along like a compass direction. Strike slip faults can have either of 2 directions of fault displacement. When you look across the fault, have the features on the other side move to the right or the left relative to your position. So if you're standing on the San Andreas Fault, it doesn't matter which side, everything is moving to your right. So if you stood right here and looked, everything moved right. If you stood right here and looked, everything moved right. So it's called a right lateral strike slip fault. The Motagua Fault in Guatemala is a left lateral strike slip fault. So if we were these guys looking towards us, everything moved to our left. And from our perspective, you know, this canal, everything moved to our left. The Pikwang Fault in China is also a left lateral strike slip fault. Transform faults are common along mid-ocean ridges. It's hard to see in this image, but mid-ocean ridges don't occur in just straight lines. They don't expand at the same rate all the way up. So this differential in expansion rates along it actually cause a development of these strike slip faults. So you'll get offsets of mid-ocean ridges all the way up through the mid-ocean ridge system. So how does all this apply to mountain building? Note that the roughly north-south trends of the mountains in North and South America and the roughly east to west trends of the mountains in Eurasia. So we've got the North American Cordillera, which includes the Rocky Mountains. It's very north-south. The Andes are very north-south. Appalachians are, you know, northeast-southwest. But then you've got the Alps. You've got the Himalayas. These are all east-west kind of in their orientation. And then you've got your younger mountain belts in the pink and your older mountain belts in the purplish. And then we've got what are called our shields. Shields are areas of exposed Precambrian crystalline rocks. So these are the oldest rocks within the continental material. They're over 1 billion years old. And then the gray areas are stable platforms. So this is where the basement or Precambrian rock has been covered by sedimentary units. So most of the U.S. are stable areas of sedimentary rocks on top of shields. When we talk about mountain building is the process of orogenous or orogeny. This is what produces mountain range. Subduction and tectonic plate collisions create most mountain ranges. So when we talk about mountain building, continuous subduction of oceanic lithosphere results in the development of thick units of continental-like crust on the overlying plate. Island arcs may be accretion, or joined together to create a terrain of continental crust. A terrain is a crustal fragment transported by plate tectonics. They can be microcontinents, islands, or island arcs. So how does this apply to mountain building? Well, for example, the Andean mountains are mountains that were built by subduction of oceanic plate beneath continental plate. So as the oceanic plate starts to converge with continental plate, it begins to subduct, and the partial melting creates a volcanic arc, and the compressional forces of the subduction also start to compress the crust material that exists here into folding and uplifting. So the subduction ends, so we have some sort of break in the actual melting of the oceanic lithosphere. So we have a reduction in volcanic activity. Volcanic activity has dropped off. And we get what are plutons. Remember we talked about intrusive igneous rocks develop here. And are the interiors of our mountain ranges. So plutons and batholiths, batholiths are just a group of plutons, begin as magmas crystallized into intrusive igneous rocks. So that was the Andean Mountains, so a volcanic history mountain range. Now the North American Cordilleran Range are mountains built by subduction of oceanic plate beneath the continental crust and the accretion of island arcs and microcontinents to North America. So we have these microcontinents and these inactive island arcs that are carried along by the subducting plate, and as they're carried along, they start to collide with our continental material. So you start to get what's called an accretion of these island arcs onto the continent. They start just sticking there. And then you can actually get a secondary subduction zone that forms seaward of the old subduction zone, bringing in your microcontinent. And then you get that accretion of your microcontinent onto the continental margin. So this is where it's not caused by volcanic activity due to the subduction of the oceanic lithosphere. It is caused by the collision of island arcs and microcontinents that are being pulled towards the continental shelf and then colliding and building up. Terrains accreted to North America in the last 200 million years. Many of the terrains along North America were once scattered throughout the eastern Pacific. So there's actually evidence of island arcs and microcontinents that have been pulled by plate tectonics to the western edge of the North American continent and collided and creating the uplift of this mountain range. Finally, the Himalayan mountains are mountains built by continental collisions. These are called alpine type mountains. So this is where you've got two continents that are just cramming together and building up and thrusting up due to that collision. So this is just showing a map view of the displacement as India collides in with China. Oh, and oops, it's important to note that an ophiolite is a mafic igneous rock from oceanic crust. I'll post a link to this video. It's just a real quick modeling of the creation of the Himalayas. And another comic strip. Okay, so that is the end of the mountain building section. I will post the next half, earthquakes, on Monday for you all. So we're back on schedule. Next week you'll have a homework that will cover mountain building and earthquakes. It's all going to be one chapter. Your discussion